OK, so last time we were talking about the massive Sudakov form factor. We're going to continue that discussion today. And we saw that in order to do this calculation, we needed to have additional regulator besides dimensional regularization. This was an example in SCT2 where we had these rapidity divergences. And so there was this additional regulator that led to these 1/8 poles in our answer, and these logs of nu as well. And we said that if you stare at these results, that you could see where you would need to take those scale parameters in order to minimize these logarithms. And it is such that in the linear diagrams, you need to take nu of order p minus. And p minus is the hard scale. And you want mu of order m, which is the scale of the hyperbola. And in the soft, you want nu and mu to be the same size, and in both of order m. So what we'll do in a minute is so you can imagine what happens next. You add some counter terms, remove these 1/epsilon poles and 1/eta poles. You're left with something that's a finite result that's a function of the cutoffs. And you put things together. When you put things together, the cutoffs should cancel out of the physical observable, which here was the form factor. So the form of the factorization theorem for this, so you have some hard function. It's just the Wilson coefficient. Some linear function, which I'll call Cn. Cn bar. And then some soft function. And so it's the usual story in some sense, but we have this additional dependence on a parameter nu, not just mu. OK, so this same statements I was making up there are kind of encoded in the arguments. You want mu to be of order m, you want nu to be of order q, mu to be of order m, nu to be of order q, mu to be of order m, and nu to be of order mu, which is of order m. So I could have written nu over m here as well. OK, and then there's also some hard factor that really lives at the hard scale. So renormalization and we have two cutoff parameters. So what we'll have, therefore, is we'll have a renormalization group for these objects in a two-dimensional space, mu and nu space. And we'll need both of those to sum the large logarithms. So just having renormalization group in mu will not be enough to sum the large logarithms in this problem. So let's, even before we, so we'll go through it and we'll write down anomalous dimensions in a minute, but even before we do that, let's just picture what we want from the running. So here's a two-dimensional space where we want to do that running. So let's put mu on this axis and nu on this axis. Break out the color. So we have some hard degrees of freedom that we're integrating out, right? But they live somewhere in this picture. So let's say here we have mu of order q. The hard degrees of freedom, as I wrote over here, they don't depend on nu. We talked about that last time, and one way of seeing it is nu is just a parameter that distinguishes modes within the effective theory. It's a regulator that was needed to distinguish soft from collinear, but if you added up these contributions, the nu dependence and the 1/etas all cancel. So the hard degrees of freedom only depend on mu and q, and so they don't care about nu, so we can draw them as a line. It's hard. They don't live localized in this space. But the other modes, we could put a dot associated with each one of them. So mu of order m here, mu equal m. Mu equals q. So and then we need to have a low energy mu scale, mu equals m. So the soft modes are going to live at mu equals m, nu equals m. And then the collinear modes are going to live over here. And the way we've set up our calculation, we sort of had one cutoff for both the Cn and Cn bar, so they both live at the same point. It could have been more fancy, but that suffices for doing the calculations here. So they both live at nu equals q. We basically had we didn't care about whether it was p minus or p plus. We regulated them both with nu. OK, so to do the renormalization group, this is where the modes want to live. But we need to connect them because in this formula, they all have the same mu and nu. So the general thing that you could imagine is that there's some point mu and nu in this space, right? And that you write down this formula there. But then everybody has large logs because you're not at the right point. And so you have to do a renormalization group evolution to that point. So the most general thing that you could think of would be that there would be a renormalization group of the hard function down to that point. And that's just the whole line moves down. So this would be some evolution kernel UH that would run from some initial condition, which I'll call UH. I'll call this mu equals mu h, and I'll call this guy mu light. Call this guy nu light. Call this guy nu heavy. Just have some names for them. And then these guys here would have running in 2 dimensions, and you have to take a path from this point to that point. And so here's a simple path. Just go over and then up. Just go over, up. And there'd be an evolution kernel associated with each one of these things. So this mu1 would be some kernel mu n that would run from mu light to some mu. And then it's at fixed nu. And this guy here would be some other evolution kernel, which I'll call v because it's running in nu space. So some collinear evolution kernel that's running in nu from some nu heavy down to nu. And it's at fixed mu light. And then there would likewise be kernels on this side. There'd be a mu s and a vs. OK, so that would be the sort of general thing that you could possibly imagine. Now, the choice of this point is arbitrary, and you know that effectively that there's consistency in the sense that you can move that point around and nothing changes. Right? So you can use your freedom to pick this point to make your life as simple as possible. If you pick it up here at the hard scale, you don't have to do any UH running. If you pick it over here at the collinear scale, then you don't have to do the collinear running. So we can do that to simplify things. And that's, again, just the freedom, the usual simple freedom of either running the coefficients or running the operators. And it's just a little more complicated. That's what this freedom to move this point around is. So this is like running coefficients versus operators. It's just a little more complicated because we have these 2 cutoffs. So let's just pick, for example, mu and nu to be mu light and nu heavy. So that's putting it over here at the orange point. Then you would just have evolution kernels. The softs would just have to run all the way over there. So you wouldn't need us either. So you would just need nu s, vs. So you have vs. And vs would run from starting at nu light over to nu heavy. So this is the initial condition. and this is the final, and it's at fixed us. And then you'd have a running from UH down to mu light from mu heavy. Okay, so then you just have these two evolution kernels, so it'd be pretty simple. So there's a consistency of both moving around in the new space. When I move this point around, there's a cancellation between Vn and Vs, and there's also a cancellation between the three U's. So there's also, in this thing, there's a path independence. So I drew a particular path where I went like that. I could have drawn another path. I could have gone up first and then over. And because the parameters nu and mu are independent parameters, the choice of the path doesn't matter. We'll see that from our calculations as well in a minute when I write down the anomalous dimensions. But this is just following from the fact that they're independent parameters. And effectively what that means is if you think about taking derivatives, you can switch the order of the integration of the derivatives. So mu d by d nu and nu d by d nu is the same as nu d by d nu, mu d by d mu. Okay. There are examples of effective field theories where you would set up cutoff parameters and this wouldn't be true. You'd think maybe you have two cutoffs, but actually you only have one. There's an example of this in our QCD where if you try to draw things in 2 dimensions, you find out that there's really only one path that the effective theory picks out. But in this case, there really are two cutoff parameters. OK, so let's do that in detail by going back over here to these formulas, writing down the counterterms, deriving from those counterterms the anomalous dimensions, and then we can see how you would derive these evolution kernels in this picture. Yeah.
Can you comment on why sort of this works, even though the mu and the nu and the collinear sectors aren't like factorizing? Like for example, why couldn't I just right off the bat draw a bunch of regulators and never have a factorization theorem, but run in different scales? Like this seems like it's sort of too easy.
Yeah, it seems too easy. It's really because if you like there's a certain, if you think about renormalization theorems, which we know much better for mu than there's not really that much known for nu, there is kind of a renormalization theorem here that is related to the fact that this divergence is really related to that iconal propagator that we had. And even when you go to higher loop orders, there's a certain universality to that propagator that's making this whole thing work. So, yeah. I think this is a relatively new thing, and I think it hasn't really fully been explored. So there's probably some interesting work to do there. All right, so let's do it and see what counterterms we get and how things work out. So we're going to do the standard thing, think about renormalizing the objects. So we'll have bare objects and renormalized objects. Each one of these guys corresponded to a single collinear field. So there's some wave function renormalization factor, and then there's some vertex, there's some renormalization for the operator. And together those two things will take us from the bare to the renormalized. And likewise for a soft guy. In this case, we just have Wilson lines, so there's just a renormalization of the object. And this guy here is the usual wave function renormalization, which is the same in SCT for a collinear particle as it is in QCD. Just for the record, there's a 1 over epsilon coming from that that'll modify our this 1 over 2 epsilon here when we put it together for the z factors. So what are the z's? So taking those graphs and these formulas, find the following. I think I dropped something. There's this pesky factor of w squared that we talked about last time. But we'll need it for this calculation. So we simply just subtract all the poles. Minimal subtraction. So I'm always going to only just write Zn because Zn bar is really the same. We set up our kinematics symmetrically so that it's really, there's no difference between Zn and Zn bar. So there's a minus sign, plus sign there. Comes a 3/8 epsilon. So those are the counter terms that we get.
Did you forget an exponential and one on the over?
Yes, I did. Thank you. And we get the anomalous dimensions, again, just by demanding the usual thing, that the bare objects don't depend on mu and nu. And we can do that separately in the mu and nu. So if you like, actually a bit kind of along the lines of your question, Ilya, there's an assumption built into this, the way we wrote this, right? I've kept the full epsilon dependence in my 1 over eta pole. And that's related to saying that I can really think of doing all the eta renormalization first, and then think about doing epsilon second. So we've built something into this that's non-trivial.
Just that the order is the same sequential.
You mean that the order being?
Like that you could do the one RG before the other. And
Yeah.
like
Oh, that the order doesn't matter. Yeah.
That seems like
Yeah.
something that you would get from a factorized expression.
Right.
This isn't factorized.
Yeah. It kind of is factorized, but it's hidden, right? Because we are saying that this is kind of a multiplicative thing on that whole thing. And that's the kind of factorization, although it looks kind of like a non-factorized thing. So let's talk about mu anomalous dimensions. And you'll see that in order for this to be true, you also don't, it's not the case that, your mu anomalous dimension needs to be independent of nu, for example. So this kind of, it looks like it's not factoring, but magically it is, in the sense of this path independence. So what is gamma mu for the soft function? So we just say that mu d by d mu on bare things is 0, and so is nu d by d nu. So that's the way that this works, and that gives us this kind of standard formulas that we're used to for the anomalous dimensions. So zs inverse mu d by d mu of zs with the appropriate sign is the anomalous dimension in mu. That comes from this equation for soft function. So if we look at that and we work it out, so if you look at this term, it actually doesn't contribute, because in this term, alpha s of mu times mu to the 2 epsilon is mu independent. So that term has no contribution to the mu anomalous dimension. And then this term does contribute, and there's a contribution from this term where you differentiate the alpha. You get a 1 over 2 epsilon. You differentiate this guy. And there's a if you differentiate the explicit log mu, there's also a 1 over epsilon. Those 1 over epsilons cancel. Okay, so there's no contribution from this guy. There's no contribution from differentiating the alpha in this guy or the explicit log in this guy. So the only contribution is taking the alpha, differentiating it, getting a 2 epsilon, and multiplying that 1 over epsilon. So the sign switches, and there's a 2. And I set W to 1. Yeah. W. Renormalize W. Statically 1. So likewise for the other case, for the collinear, and this is actually the same as gamma mu and bar. And what this gives, if you solve the anomalous dimension equation, so the anomalous dimension equations are like with my sign convention, like this, or etc. So you would solve those equations, and those equations would give you the kernels, US and UN. And it's a simple multiplicative RGE, so you just, this is mu d by mu of log S, and you just integrate in the way we've done before. And consistency says that you could run this in this picture either way, and that is a relation between the anomalous dimensions. There's also an anomalous dimension for the hard function, and if we add them all up, we get 0. We pick the sign conventions accordingly, so you could write the relation that way. And so you can calculate the gamma h by knowing these three, gamma for the hard function, or you could calculate it by the counter term for the hard function. And as expected, it only depends on a log of mu over q. There's no news in that. So that's the mu anomalous dimension. It works as usual. And the interesting thing is that there's also a new anomalous dimension, because the Baire functions are independent of nu. It's the same type of formula. We just have nu d by d nu instead of mu d by d mu. There's no nu dependence in the coupling, alpha, but there is a nu dependence in this w. When you differentiate the w, you get an eta. And that's where basically the contribution is coming from. So what happens is you differentiate the w. That kills this eta. But then it looks like your result would have a 1 over epsilon pole. But you also have to differentiate explicitly this nu here. Again, that has a 1 over epsilon pole, so those two cancel. Once you take the epsilon goes to 0 limit, they cancel, and you're just left with a finite anomalous dimension. So when here I'm always sending epsilon to 0 and eta goes to 0, and that's what sets w to 1 and stuff like that. Okay, so this guy. So there's cancellations in 1 over epsilon poles to get those results, and then there's also cancellations of 1 over epsilon poles to get these results. And equations like nu by d nu of S is gamma nu, S would give the kernel vs, etc. Okay, so there's the explicit anomalous dimensions. Let me keep that picture up. So if you ask what path independence means, you could say path independence could be phrased by the fact that I could take Z inverse and I could take a commutator of derivatives, right? Because I'm saying that either order should give the same result. And if either order gives the same result, that must be 0. And what this formula says, at the order that we're working, is that you can take mu d by d mu of some, say, new anomalous dimension, and that should be equal to nu d by d nu of the mu anomalous dimension. That there's a connection between the two things. And if you look at the factors, and if I wrote everything down correctly, then that's true. And likewise for the linear. So this is the statement of there not being a dependence on the path. These are formulas that have to be true if that's going to be true. So I'm not going to write down all these kernels for you. There's a lot of them. But just to give you a flavor for what the solutions look like, they kind of look familiar. Let me write down a couple of them. So I'll write down one. I'll write the ones for the soft. So at leading log order, what would they look like? They're exponentials, Sudakov logarithm type formulas. They're not the same precise formulas that we had earlier, but they look kind of similar. Let me write them down, and then I'll talk about them. So these are running along straight paths. And they involve ratios of alpha, basically, as that's what the running coupling is doing. So you could always write things in such a way that you don't have alphas that involve nu, right? Because the RGA just has alphas of mu. And so if you like, when you're solving the nu anomalous dimension, this equation is very easy to integrate because there's no nu's on the right-hand side. You just get a log of nu. And that's why that's why we have this kind of simple log nu here. Here I wrote alpha, 1 over alpha of nu s, but I could have write that back in terms of a log. So it really isn't. That was just convenient to make it a simpler formula. So if you write down the evolution kernels like that, they'll satisfy this, these multiplication properties that this figure implies. And I won't go through that. But it's kind of neat to see how it works out. All right, so that gives you an idea of how we would sum logs for this Sudakov form factor with these two cutoffs. We just have the evolution kernels, and we use them as usual, but we have this more complicated picture of what type of renormalization we have to do. And you can think about also if you wanted to, for example, say you wanted to do this in some calculation, and then you calculate it up to some order, solving these anomalous dimensions, and then you wanted to vary scales. Well, now you have a two-dimensional plane to vary scales in, right? So If you're varying the soft scales, you can kind of move around in a box around this guy, where you're varying both nu L and mu L by kind of factors of 2. And so they're doing uncertainties in this kind of setup would be, you'd have more parameters to vary than you would usually have just with mu's. But really, it's just a straightforward generalization of the one-dimensional picture of mu evolution to a two-dimensional picture of nu evolution. And the interesting part is the overlaps between these parameters.